If we are asked to solve a triangle, given an angle, the side opposite from that angle, and one other side, we can go ahead and draw a diagram. So I've set up the angle that I'm given as a base angle, and then A is going to be the side opposite from it. We can use the sine law because we can see that we have a pair of opposites here. So I'm looking for the measure of angle B, which comes out to be about 61 degrees. But remember, if we go back to cast, I know that sine, my sine ratio here, is going to be positive in either quadrant 1 or in quadrant 2. So we could have a 61 degree angle, which we have here in this triangle, or if we have an obtuse triangle, we could also have a measure of 119 degrees. Angle B can be 61 degrees, or angle B could be an obtuse angle of 119 degrees, and then in each of those cases, I can solve for that third angle C. Because I have a positive sine ratio in quadrant 1, where my angle will be less than 90 degrees, or in quadrant 2, when I will have an obtuse angle, I can have the potential of two different triangles that have these measurements. One is an acute triangle, the other is an obtuse triangle. So we need to be aware when using the sine law of the ambiguous case. This scenario will only occur if we have an angle that's given to us, if we have the side opposite that angle that's given to us, and if we have this side here that's given to us. So we refer to this as angle, side, side. We always need to be thinking carefully about the information that we're given and what that means. So if we have an obtuse triangle, we know an obtuse triangle has one obtuse angle. If this angle that we're given is angle A, the side opposite from angle A, this side here is shorter than the adjacent side, we can see that this is not obviously going to connect. We have no triangle. There is no solution in that case. If from angle A here, the side opposite this is greater than the side adjacent, we can see that this is going to allow our triangle to connect. There will be one solution for that particular triangle. If we have an acute triangle, three angles less than 90 degrees, the first thing we want to do is calculate what is the height of that triangle using the information that we're given. So let's say we're given angle A. If the side opposite from angle A is less than that height, we can see that we're not going to be able to actually connect that triangle. No solution will exist. If the side opposite angle A is equal to the height, we have one solution. That height is just side A. If the side opposite angle A happens to be longer than the adjacent side, we'll also see that there's only one way we can draw this triangle. I'm not going to be able to take this side and swing it around here and have that angle be the same in both cases. If the side opposite angle A, so this is angle A, this is the side opposite, is longer than the height. So you can see here's the height, this is longer than the height, so we can connect and create a triangle, but it's shorter than this side adjacent to angle A. We can also take that side here and then swing it around this way, and you'll see that gives us the second triangle with that obtuse angle. If I'm given an angle, a side length, and another side length, this is my third side length, that does not necessarily prove congruency, because as you can see here, I can connect my triangle like that, that's one triangle, and then I can take that same side length and swing it around like this and get clearly a second triangle that is not congruent to the first one. So if I know the angle measure is the same, this side length is the same, and this third side is the same, because I can either have a triangle like this, or I can have a triangle like that. So if we're using the sine law, we have to be aware different solutions may exist. We can have no solution, we can have one solution, or we can have two solutions. So if we're given an angle, a side, and a side, start by setting up the angle that you're given as the base angle. We're going to then know that side opposite from it. Leave the base of the triangle as the unknown measure, and then we're going to fill in the other side here. So we're going to set up angle, side, side. We can look for the height of the triangle and then see, is this side able to swing around, creating two different triangles? All right, so given the information, the first thing we always want to do is draw a sketch. Now, none of these will be drawn to scale, but you want to try to get it as close as you can. So for example, we can see that we have an acute angle here. So we're going to set up angle A as the base angle, and we're going to draw in that acute angle. I know that side A has to be opposite angle A, so that means this is 24. We're going to leave that base with the unknown measure, and we're going to take this other side and put it here, so that if there isn't second case, we'll be able to catch it. And then the first thing we're going to do is calculate the height of that triangle. Because I now have created a right triangle, I can go ahead and use a primary trigonometric ratio. So from my angle, I'm looking for this side opposite, we know the hypotenuse is 42. So the height of that triangle is 21 centimeters. And then we can take a look and say, okay, 21 centimeters is less than this. So in this triangle here, we know the hypotenuse has to be the longest side. So we can create a triangle. And this side is shorter than this side here. So it could swing around and we could get a second case. Our goal is to solve the triangle. So in the first case, we can see that because we have a pair of opposites here, the first thing I'm going to do is solve for angle B. So I can take the sine of angle B divided by the side opposite, and then my only pair of opposites is right here. So if I begin with an angle on top, I continue with an angle on top, so we can set up the sine law, cross multiply, divide by 24, and then we're going to take the inverse sine in order to get angle B. So we now know angle B. In order to get the third angle, I can subtract the two angles that we know from 180 degrees, and that will give me angle C. In order to solve for the last side, we can see that side C is opposite angle C. So again, we can use the sine law, and now we've solved the triangle. We have 3 angles and we have 3 sides. And now we have to solve for the second case. So if we take a look here, so we've already established that angle B is the 61 degrees. So if we took this side that was over here and we swing it around here, you can see that if we were to draw this in like this, we have an isosceles triangle because this side is the same length when we put it over here. If this is an isosceles triangle, those two sides are the same. These two base angles are also going to be the same. So if this was a 61-degree angle, I know this is also a 61-degree angle. So we can see that we have a straight angle here that is 180 degrees. So I can go 180 degrees, take off that 61 degrees, and now the interior angle of my triangle, angle B, is going to be that obtuse angle of about 119 degrees. And now we can solve for that third angle by taking the sum of the interior angles in a triangle, subtracting those two angles that we know, and we can get the third angle. And now we also need to solve for side length C, because you can see it's not as long as it was in this acute triangle. It's going to be shorter when we took the side that was here and swung it back along here. So now we know that angle C, we're looking for side C opposite from it, and we again have that other pair of opposites. So we can set up the sine law, and side C down here now has a measure of about 25 centimeters. And then just quickly check your work. So we know that the largest angle is opposite the longest side. The smallest angle is opposite the shortest side. And then over here, the largest angle is opposite the longest side. My smallest angle is opposite that shortest side. In our next example, we're given angle C is 82 degrees. So again, I'm trying to draw this as close to scale as I can. So it's a little bit less than a 90-degree angle. So side C opposite from it is 7 centimeters. And then if I take the other side that I know and put it here so that we leave that base blank, this is 11 centimeters. So already I can see if this is 11 centimeters, given that angle, it doesn't quite look like we're going to touch, but let's go ahead and find out. So let's see what the height of that triangle would be. And if you take a look at this triangle here, so we have a right angle triangle. In a right angle triangle, my hypotenuse has to be the longest side. My hypotenuse would be 7 centimeters. When I calculate the height of this triangle using a primary trig ratio, so 82 degrees, we're looking for the opposite. We know the hypotenuse for that one. We end up with a height of 10.89 centimeters. So this is the longest side in this potential triangle, which means that our overall oblique triangle does not exist. There's no solution. Now let's say you didn't catch that right away and try to carry on with solving the triangle. So if we're looking for this measure angle A, we can see it's opposite side 11, so we can go ahead and set up the sine law using that other pair of opposites that we know. And when we get the sine of angle A, that ratio is 1.556. So right away you know that there's a problem because the sine is the opposite side divided by the hypotenuse side. If I get a value of 1 point something, that means my opposite side is greater than the hypotenuse. My numerator is larger than the denominator. So that's not possible. And then even if you carried on and tried to take the inverse sine, your calculator is going to give you that error message. In our next triangle here, again, set up the angle as the base angle. That makes this side A, and then put the other side right here. First thing we're going to do is calculate that height. And when we do that, we end up with a height of 6 centimeters, which is equal to this side opposite. So that means this side opposite is actually the height, and we have a right triangle that we're trying to solve. So let's get rid of this and actually draw a proper right triangle. So if we're looking for that third angle, if this is 30 and this is 90, subtract those from 180, and we can see that this is 60 degrees. And now we need to find the measure of that third side. Now you could use a primary trigonometric ratio. So from our angle that's given, we're looking for the adjacent side. We know the opposite, so we could use a tangent, or we know the hypotenuse, so we could use cosine ratio. Either of those will work. Or if you recognize this is a 30, 60, 90 triangle, that's one of your special triangles. In our 30, 60, 90 triangle, we know that the side opposite the smallest angle has a ratio of 1 to 2, short side to hypotenuse, and we can calculate that third side as the square root of 3 using Pythagoras' theorem. And then I'm going to put the a here because we could also have any multiple of that. So in this particular case, if I know that this side C, opposite from angle C, this is what I'm looking for. I know that's equal to the square root of 3a, and then we can see that 1a is 6 centimeters. So I'm going to have square root of 3 times 6, which is just 6 times the square root of 3. Now, if you wanted to use a primary trig ratio, so let's say we use cosine. Cosine of 30 is adjacent, that's that side C, divided by the hypotenuse. That's going to give us a value of 10.39, etc. centimeters. If you put this into your calculator, you're going to see that those are equivalent. So this is the answer. This is an exact value. Anytime that you're given an angle, a side, and a side, set it up so that your angle is here, the side opposite from it would go here, and then if you have a choice as to where to put the other side, put it here so that you can catch if there's two potential solutions. If this one side could potentially swing around the other side. Also be aware that no triangle could exist, in which case there is no solution.